Hi there, and welcome to session 6 of the Bridgetech online training sessions. Today we're going to be looking at intelligent redundancy. Now, intelligent redundancy comes in two devices. One is purely for ASI. So in other words, we switch ASI inputs to one single ASI output, depending on ETR290 monitoring, in other words MPEG transport stream monitoring. And then there's the satellite redundancy, the so-called VB273, which takes it one level further. It does all of the ETR290 testing that we're used to with the 243, but it adds an RF layer at the end. So basically it monitors the output of an A and a B modulator and makes a switch depending on an ETR290 alarm or an RF alarm. So this is the VB243 blade. We can see it in when we look at the web interface in a moment. I'm just showing you the slide so that you can see what it looks like and the difference between the 243 and the 273. So the 273 is, as I said, the satellite redundancy. We'll be looking at these in far more detail, but I wanted to show you the concept behind redundancy switching. So we would normally have a main and a backup feed. This again is the 242, 243 ASI redundancy switch. Now I think this diagram might be slightly out of date. There is often two completely different encoding and multiplexing chains, and these can often be cited in a disaster recovery site. This does happen, but in a head end, what is more usual is you will have a number of encoders, one or two spare encoders, and then they will both feed, all of those encoders will feed into a main mux and a backup mux, and that type of redundancy scheme tends to be in a single head end. And that may well be completely duplicated in a disaster recovery head end. So the diagram's slightly misleading, but nevertheless it works exactly the same way. So we have the output of MUX 1 going into the 243 card and the output of MUX 2 going into the other input of the 243 card. And the middle BNC connector is the output, and that would tend to go to a modulator. You can see that the 243 card also feeds back to the 242 card, and this is where the testing is actually done. So it won't surprise you to find out that the satellite setup is exactly the same. The only difference here is that we actually take the modulator output. So we take L band or IF depending on how the modulator's set up, and then we have an L band or IF output, and that will go to either an HPA or an up converter. We will upconvert the intermediate frequency to L band and then input that to the 272 card. And exactly the same process occurs, except there's one extra layer, the RF layer. So that said, let's actually see how this works in practice. Okay, so we're going to be looking at a 272, 273. In fact, technically the chassis is called a VB273. And just a word of warning, you can't buy a 273 card and put it into a chassis with a 120 and a 272 already in existence. Unfortunately, you can't buy it that way. You have to buy the entire unit, and that's because the VB272 is not a standard VB272 card. It has had a couple of modifications. So the 273, the VB273 as a unit is purchasable as a 1RU unit with all of the cards populated. I'm not going to be showing the 243 because it's functionally as identical. The way it does the switching is exactly the same. So let's go straight to the redundancy tab here and have a look at how this is set up. I'm going to just get rid of the bottom screen there of the alarms. Firstly, we've got three modes, three redundancy modes, and you can see that currently output B or rather multiplexer B is currently switched to the output. So input B is switched to the output. Now we can choose the input. The input currently is set to input B, as I said, and it's a manual mode. And this gives you a little explanation. The manual mode is input. The switching can be performed by either using the hardware buttons. Just to go back quickly and show you, there are hardware buttons under each input. So we've got input 1 and A input and B input. And you can, in manual mode, you can press those little buttons and they will switch the input to the output. They can also be switched using the web interface. So I can click on the web interface and I make a near seamless redundancy switch. It is, by the way, a hardware relay, and it's a locked magnetic relay. So even if the device loses power, the output won't switch, or rather the input won't switch. So it is locked. And down the bottom, before we go any further, this return delay in seconds, which seems in this particular device to be set to an unfeasibly high number, nevertheless, this delay is calculated and no switch, no automatic switch will occur from A to B in that number of seconds. This is obviously to stop fluttering between AB, 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 and this can be set to a more reasonable number in a production system, of course. So I can switch back to B very easily. So this is manual mode. So an NMS system, so something like Data Miner or some custom written NMS could actually come in using the EII, the External Integration Interface, and also make the switch. This is what we mean by manual mode. So let's change the mode just to have a look. And we'll go to super local for now and apply. Now you can see that we're still on B. Super local is called up in the panel here, and super local mode can only be formed by the hardware buttons and the GUI. So I can make a switch back to A, and I could go onto the buttons and press A, but no other mechanism is available for switching. So that super local means on the probe itself. No NMS can come in and do anything about it now. So basically we've got two manual modes. We've got the manual mode and the super local mode. But most people are going to be interested in the automatic mode. So we'll switch to the automatic mode, and the first thing you probably notice is that the A and B switch buttons at the bottom have disappeared. So now we're in full automatic mode. Interestingly, the probe says it will wait for that unfeasibly large number of seconds, which is counting down if you notice, before it makes a switch. So let's look at the display underneath. The display underneath, the status for input A and the status for input B is currently showing all green, so that's good. So we're not having any problems that might cause a switch. So we're looking at ETR priority 1, and we've already looked at ETR testing in a previous session. So I'm not going to go into ETR testing per se, but I only as far as it pertains to the operation of the switch. Now, if we look down column 1, priority 1, you'll see that the PAT has got a little unusual symbol there. It's half green and half grey. And what that means, quite simply, is that we are checking for alarms, but we will not make a switch on a PAT alarm. However, if we look at the continuity counter below it, that is entirely green. So that means we are monitoring the continuity alarms, and we will make a switch if we get a continuity alarm. Going down to the PMT again, that's half green and half grey. So we are monitoring it, it will raise an alarm, but it will not cause a switch. Missing PID below is completely grey. And this basically means exactly the same as it does in standard ETR testing. Grey means we're not testing. This is quite subtle actually, and I did mention it before. We are testing because you can still see measurements, but it will not raise an alarm in the probe, and because it doesn't raise an alarm, of course it won't raise a switch. So effectively this alarm missing PID is ignored, as is the conditional access table alarm and all of the other grey alarms. None of those will cause a switch, nor will they raise an alarm. So moving over to where the difference between the VB273 satellite redundancy switch and the VB243 ASI switch are different, it's in the interface. So the interface, of course, in a satellite probe is the satellite demodulator card. And so we're monitoring these signals. In fact, we're not, because it's grey, post low density parity checking is not being alarmed. So that won't cause a switch. But the modulation error rate below it and the signal to noise ratio below that will all cause switches, and you can see these all the way down. T2MI, this is a satellite probe, so T2MI is not applicable. But EBN0 and EVN, they are, but they won't cause switches, but they will raise an alarm. So that's interesting. And if you notice, looking over to status B, we have a different set of circumstances. So if you notice, PAT and PMT in priority 1 testing will both cause switching. Now, this is a peculiarity of the way the VB273 is set up. You wouldn't normally expect this in a production system. I would expect to see input A and input B to be identical, because then it would switch in an unpredictable way. But it is possible to do it. So let's see how we actually set this up. So we need to go, by the way, before I continue back to ETR 290, we can look at the satellite 1 and satellite 2. Of course, the VB272 card is actually monitoring a single frequency, and that is the frequency of the modulator, of course. So moving to ETR 290, we can see that we have only 2 micro ETRs, SAT1 and SAT2, unsurprisingly. If we move to the ETR threshold, you'll see that we have all the default thresholds that come with a probe, and we also have 2 additional thresholds, redundancy input A and redundancy input B. So let's have a look at one of these. Now I think you can see the difference between the standard ETR setup and the redundancy ETR threshold. So first of all, we look at priority 1, TS sync. We've got an alarm, and the alarm is active, and we are making a redundancy switch on this particular parameter. Now, if you remember, the PAT for input A was alarmed, but there was no redundancy switch. I'll change that now and we can see the difference. So I apply the changes, close, and if I now go back to the redundancy tab, you'll see that the PAT has now turned completely green, because we're monitoring the PAT for an alarm, and we will make a redundancy switch if an alarm is raised. I will go back and change that back, because that may be on this demo probe set for some reason. So I'll just turn that off again. And it's the same all the way down. You can choose which parameters cause an alarm and which parameters will cause a switch by clicking in the redundancy box. And if we go all the way down to the interface checks, you can see here are the RF checks that are made. And of course it says signal strength, and all I can see here is alarm, and that's because the ETR 290 testing is referring to the RF thresholds to set the level at which an alarm occurs, and therefore a switch. So as well as setting this up for input A and input B, you need to go back to SAT1, go to the RF threshold and the redundancy parameter, and choose the redundancy threshold. And here's where you set your levels, and we covered this in full detail on the WebEx about RF probes. So I'm not going to go into these into much detail now, only to say that these levels then would cause an alarm to be raised and a switch from A to B to occur. So we won't change any of those. You don't need to do the same thing on SAT2 because it's exactly the same thresholds. The thresholds are shared between both satellite inputs. And if we look at the redundancy threshold itself, we can see that there are two references, and of course this is SAT1 and SAT2. You do need, when you're doing the tuning setup, when you're setting the, this may seem like obvious, but I will mention it just in case. When we put the tuning in for the particular modulator frequency, we do need to set the ETR threshold and make sure it's set to redundancy B, because this is SAT2. And also, of course, the RF thresholds also need to be set to redundancy. But apart from that, it's very similar to setting up an ordinary satellite probe. And the VB243, the ASI probe, of course, exactly the same steps need to be carried out, but of course there's no interface checks to be performed, so you don't need to do any of that. But you do need to set up all the ETR testing. So that's really it. Everything else in the probe is redundant. Although, having said that, of course, the VB120 is still sitting there. It's not normally advisable to use a VB273 redundancy probe or a VB243 ASI redundancy probe. It's not normally advisable to use it for anything other than redundancy switching. Redundancy switching, remember, is service affecting. So it is actually in the signal path, and it's a crucial element to that redundant system and that transmission system. So it's not a good idea to use the probe in anything other than its redundancy mode. Okay, well that's a really quick WebEx session this week. So thank you very much for listening out, and the details of the quiz that you can take. It's a short quiz this week. Only 10 questions. Next week we'll be looking at OTT theory. We'll be doing two WebEx sessions, next week and the week after. Next week we'll be looking at OTT theory, and I'll be going, again it'll be another relatively short WebEx. We'll be looking at the OTT theory and actually how OTT works, because although it's been around for a long time, there's still a lot of uncertainty out there about OTT and how it works. So we'll look at that. And the week following that, we'll look at how our probes actually look at OTT and monitor them. So thanks for joining me. And if you're listening offline in your own time, thank you for listening. And I look forward to welcoming you again next week.